All right, good morning, everyone. So I discovered that the video I made this morning during the class lecture, my iPad had its microphone off, so I have to do it again. So this is not identical to what I presented during the lecture, but I'll try to make it as similar as possible. Okay, so the first thing to talk about is a new slide that I added to the Unit 3 slides. And this is just an introductory slide on random variables. The information here is in this handout, which we'll talk about in a moment. But so this is just starting from the beginning. Why are we considering random variables? Well, they're useful when we want to describe what might happen or what tends to happen in machine learning experiments. If we didn't have random variables, we could only talk about a specific experiment for which we have a specific data set, and it would be difficult to generalize to what might happen in the future or what we expect to happen in general. Okay, so as we discussed the other day, these things, random variables, you can think of them as a function if you like. It's something that can generate many different possible values. What we know is we know exactly what kind of values it can generate, and we know exactly how often it generates them. In other words, we know the probability of it generating those values. So we call the values it generates realizations. And when we talk about random variables, it helps to talk about two different kinds of random variables: discrete random variables and continuous ones. So let's start with discrete random variables. Let's say that we have a random variable called A. We'll be using capital letters just for now on this slide. So a discrete random variable takes values from a finite set like this. And so here I'm using superscripts rather than subscripts because we often use subscripts when we talk about realizations of this random variable. So these quantities are the capital K different things that this random variable can manifest as. So it only can be two K numbers. So for example, if I have a coin, it's heads or tails, nothing else, and so it would just have two values. Okay, so in addition to knowing what values this random variable takes on, we also know how often or what the probability is that it takes on all these different possibilities. And we can store those probabilities in a vector. There's going to be K of them. And altogether, we call this vector the probability mass function. And so again, these values, like the kth of these values would be PAK. That is the probability that the random variable takes on its kth possibility. So because these are probabilities, they must be somewhere between 0 and 1. And when you look at all the possible things that can happen, all those probabilities together, they must sum up to exactly 1. Okay, so that's what we have for discrete random variables. Now, if we have a continuous random variable, again, we'll call it A. This one takes on an uncountable number of values from the real line. Now, it doesn't have to take on all values from the real line. For example, it might just take on positive values. But the point is that there's an uncountable number of them, and so I can't even order them in a list. So for this random variable, we don't have a PMF, but we have other ways to describe it. One way is the cumulative distribution function, or CDF. And this is the probability that that random variable is less than or equal to some number A. So we have to specify this function here for all A on the real line. And together, that CDF function completely describes our random variable. Now there's another way to describe it, which we use more often in this course, and it's called the probability density function. And we use a little p for that, and this is just the derivative of that capital P function. Now with this probability density, I think one way to understand it is if you want to write the CDF at A, or the probability that random variable A is less than or equal to a specific value A, you can do this by integrating the PDF from minus infinity all the way up to A. And so here's the PDF. Notice that I'm using a different dummy variable, something different than A, because A is used to mean this, and so I can't use A here. I have to use something else. So this density is required to be non-negative, and it must integrate to 1. So the sum total of all the things that can happen must be 1. Okay, so that is kind of a review of the highlights. So as I mentioned, all this stuff is in this document, a primer on probability and expectation. And let's just take a quick look at that. So here's this document I wrote up. It's kind of like a few pages from a textbook or so on. So here it talks about random variables, talks about why we want to use them, talks about discrete random variables, and it goes through a lot of what I just went through in those slides. And then it talks about continuous random variables here. Again, things that we talked about in those slides. And a few other things too that I didn't have space for on the slide. So for example, if you want to say what is the probability that random variable A takes on something, a value in the interval between two numbers, A1 and A2, you can do this by integrating that density from A1 to A2. Another interesting thing is if you have a discrete random variable, and typically we use a PMF to write it, but you actually can write it as a PDF as well. And to do this, you have to use this point mass or direct delta function delta. So what that function does, it's kind of a weird function. It's an infinitely tall, infinitely narrow, but unit area spike-looking function that's centered at the origin. So in other words, it's going to take the value of infinity at its peak, 0 everywhere except at the origin, but crucially, it integrates to 1. So once you have that, you can actually write the PDF of your discrete random variable like this. And so maybe you have here, this would be a point mass here at, let's say, A1, and another point mass here at A2, and so on. And instead of the areas being exactly 1, you would then scale those direct deltas by the values of the PMF. So you take your original unit area pulse and you just scale it so that it has these areas. And this is how you can write this as a PDF. Okay, so other important things that are discussed here are joint random variables. So when you have two random variables, A and B, and they're interdependent on each other, we describe them by a joint PDF. This PDF behaves the same way as we would expect from the univariate PDF, so it must be non-negative, and it must integrate to 1, where now the integration is over the two dimensions A and B. Another thing, the joint probability, you can swap A and B. It doesn't matter. And an important concept is statistical independence. If A and B are statistically independent random variables, what that means is that their density, their joint density, decouples into a product of their individual densities. These are called the marginal densities. Okay. Now, once you have more than one random variable, sometimes you would like to know how one of them depends on the other, and that is most easily expressed through conditional probability. And in particular, we use the conditional PDF of A given B. And if you are thinking about what is this, so here we have the random variables on the bottom and then specific numbers here. So this quantity would mean the PDF, or the density of A, evaluated at A, given the event that random variable B takes on exactly the value little b. Okay, so that's the meaning of this. So we can relate the conditional and the joint and the marginals through this equation. And another related one that we'll often see in future lectures is called Bayes' rule. And Bayes' rule helps us to reverse the order of these two things in a conditioning statement. So for example, maybe I know probability of B given A because it's easy to figure that out from the problem statement. But maybe I would like to know probability of A given B. So what I can do is I can multiply PB given A times PA, divide by PB, and I get this PA given B. And all of this follows directly from that earlier identity, this one. Okay, so interesting point. If the variables are statistically independent, then the probability of A given B is just the probability of A. So fixing B tells you nothing different about A. Similarly, fixing A tells you nothing about B. Okay, so the other day we also talked about expectation. So with expectation, if we have a continuous random variable, we have something of this form. So here we have the density, here we have the random variable itself. And if we have a discrete random variable, we can write expectation with a sum rather than an integral, where we once again put in the possibilities of that random variable and then the probabilities at those possibilities. So you can think about this as just like a generalization to, more and more and more possibilities until you have eventually an uncountably infinite number of possibilities on the real line. So something important to talk about, which we'll talk about a lot more today, is the difference between the sample average, which we know is this, A bar. This is a sample average of a set of realizations of A, or set of numbers. We'd like to know the difference between that and the statistical average, the mean. So just to give you an example, I might have a variable where the statistical average is 0. But that does not mean that my sample average will necessarily be 0. For example, maybe I have a coin and I assign the values 1 to heads and -1 to tails. And if it's a fair coin, on average, I will have a value of 0. I'm going to have half the time I'm going to get 1, half the time -1. So on average, I get a value of 0. But if I, flip the coin, if I flip the coin once, or let's say if I flip the coin an odd number of times, 3 times, there's no way that the average could be 0. It's going to be something either greater or less than 0, depending on whether I flipped it, how the flips came out. So that's one example where the sample mean is never going to be equal to the statistical mean. Now, we might wonder, if I flip this many, many times, how does the sample mean relate to the statistical mean? Well, by something called the law of large numbers. As n increases, this sample mean should get closer and closer to your statistical mean. So you might wonder, well, how close does it get? We'll talk about that a little bit later in the context of the variance on this quantity A bar. If we think about these themselves as random coin flips that happen, then this becomes random, and I can analyze its mean and variance, and that's what we'll do a little bit later today. Here are the two really important identities that we'll use over and over again with expectation. You get a chance to practice those on your next homework assignment. These ones we discussed previously. This second independence one holds only for independent random variables A and B. It doesn't hold in general. Okay, so we have here expectation. Similar quantity is variance, the variance of a random variable. The variance of a random variable is the average squared deviation between A and its mean. So as we learned by the generic rule for if I have the expectation of some function of a random variable, then this is the function of that random variable. Actually, I need to use a little a here. And then I have the density of that random variable, dA. So that's the generic equation for any function. And here we have one particular example of a function where I subtract something from a and then I square the result. So I take that whole thing and I put that in here to take the place of this. So that explains where this comes from exactly. It's just an example of this general rule. And that's the expression, at least if we have a continuous variable or if we write our discrete variable PDF using delta functions. We can also write a similar expression that holds for discrete variables in terms of their PMF. So once again, we'd like to make a distinction between this statistical variance and the sample variance, which we described back in Unit 1. And the sample variance looked like this. You have a list of numbers, AI. You first compute their sample mean. You subtract that, and then you take the average of that list. So once again, this is operating on a list of numbers, whereas this is operating on a random variable. We can expect that this quantity will get closer and closer to the statistical variance as n gets larger and larger. But for any finite n, we don't expect that these would be the same. Okay, so one really useful identity that comes up again and again when you're dealing with variances is this one over here. So because it's quite often that you have to look at the average value of a squared random variable, it turns out that that is the variance plus the mean squared. And it's maybe worthwhile doing a very short proof of this. So here we have expected value of a squared. So what we're going to do is we're going to write a in a very strange way. We're going to subtract mu and add mu to a. Clearly that's the same as adding 0. Then we have we can think about this as a quadratic. We can expand this quadratic into the first term squared plus 2 times the cross term plus the last term squared. Then we can exploit the linearity property of expectation to say expectation of the sum is the sum of the expectations. And then we can take a close look at each term. So if this is the mean of the random variable, which here we're saying we're defining it as to be the mean, then this is exactly the variance of that random variable. Similarly, if this is mu, which is the mean, then this part cancels. And finally, this last one is just the mean squared. So that's where we can prove this rule. Okay, so we have, for random variables, we've talked about expectation, talked about variance. What about conditional expectation? So this is basically the mean of a random variable A, given that the event of some related random variable B equaling a particular number little b happens. So essentially what happens when you have a conditional expectation, it's very similar to the non-conditional expectation, is that you replace the density with a conditional density. That's really the only change. So if you think about, solving this integral, let's say you know exactly what this function is. You solve this integral. As a result, there will be no more a's in your expression, but it will remain a function of b. So just remember that this conditional expectation here is going to be some function of b. Now, sometimes people write this conditional expectation without saying that the random variable b equals something very specific. They just leave it as random variable b. So you can think about that kind of conditional expectation as just a function of this random variable b. So that itself is going to be a random variable. Okay, because it's a function of random variable, so it's random. Okay, so we've talked about conditional mean. We also have conditional variance here. And so by definition, conditional variance, you take A, you subtract its conditional mean, and then you take the expectation, again, conditional on this event. And by our what we've done before, you can see that that's going to be equal to here. So here we have our conditional density, and then over here we have the function that we are taking the expectation over. Okay, so why might this be useful, conditional mean, conditional variance? Well, we have a few applications of it. So one of them that we talked about, let's focus down here on this simpler example. We talked about this law of total expectation, which is a fancy way of saying that happens. So again, let's dissect this. So when you look at what's happening on the inside, we have a conditional expectation. We're asking for the average value of A given that the random variable B takes on some value. So this thing will no longer be a function of the random variable A, it will be a function of its statistics, but it will be a function of the random variable B. So when we take the outer expectation, this outer expectation we are now averaging over B, whereas the inner expectation did its average over A. As a result of this double averaging, the final quantity will no longer be random at all, it will be fixed, and in particular it will be the expected value of A. So we gave one example in an earlier lecture that said, imagine that A is the temperature and B is the month, and so if you say, what's the average temperature in Columbus given the month? Well, clearly, if I tell you exactly what the month is, like, January versus July, that's going to cause this to be quite different. But here, we're just going to get essentially the average temperature, but this is still going to be dependent on the random variable of month. So it depends on how the months are distributed. We might say all months are equally likely. So this is going to be a random quantity, but when we finally average over the months, that's like saying what's the average temperature given the month, and then you average over the months, you're back to the average temperature. And we can do a short proof of this if you like. So we first have an outer expectation over B, which looks like this, and then the inner conditional expectation, A given B, looks like this. So the first thing we can do is just get rid of these brackets and reorder our integrals, move A to the outside, B to the inside. We get this. And then we can use the fact that probability of A given B times probability of B is the joint probability. And then we can look at this inner integral. I have the joint probability, and I'm integrating out one of them. That brings me back, that integrates it out completely, and now I just have the marginal probability over A. And when you look at what we have here, this is just, by definition, the mean of A. Okay, so that's one application of conditional mean. But there's another important application which we used for the bias-variance equation, which is minimizing MMSE, or minimizing MSE. So in general, if I have some target variable y and some features x, and I want to come up with some function f that predicts y from x that is optimal in the sense of mean squared error. And suppose that I happen to know everything about y and x in terms of their statistics. So this is different from machine learning, where no one tells us the exact statistics of y and x. They just give us a bunch of samples. But imagine that we know a lot about some application, and we can actually build these models, and we can therefore confidently say, I can give you the very best predictor, the one that minimizes the mean squared error, and let's see how we do that. So this is the mean squared error. This is the difference between y and our prediction squared on average, where we're taking the expectation over all x and all y. Okay, so what we're going to do is we're going to do this in two stages. First, we're going to look at the mean squared error for a fixed set of features x. So we're going to do that by conditioning on x and defining the mean squared error as a function of x. And once we're done with that, once we know what that is, we could, of course, take our final expectation over x to get back to the mean squared error above. So this inner expectation is a little bit more tractable to deal with. So let's find the function f that minimizes the MSE for a particular x. Okay, if we want to do that, here's our mean squared error. We have to simplify this a little bit. So the first thing we can do is expand out this quadratic. We get y squared minus 2 times the cross term plus fx squared. We can use the linearity of expectation to write this as a sum of these three things. Notice that because we're conditioning on x, this last thing is deterministic, as is this. And so our expectation is only on the y quantities given x. So what we want to do, again, is we want to find the f that minimizes this. So we can take our favorite approach, which is to find the value of the unknown that sets the derivative of the cost or the loss to 0. So in particular now, we look at the derivative of MSE with respect to this function f, and we say, what is the predictor, we'll call it f hat, that sets that exactly to 0? Well, this derivation is actually very straightforward. We just have to differentiate this with respect to fx. So the first term goes away, the second term just gives us this, and the third term gives us 2fx. So we know that this must equal 0, and we just rearrange a little bit to find that the optimal f is what we call the conditional mean. It's the average value of y given x. So this is a super important result from estimation theory. Now the second question we could ask is, assuming I can find this f hat, how good will my MSE be? What is my minimum possible MSE given x? So in other words, we want to evaluate this expression. We're plugging in f hat, the optimal one here. And so again, we know what f hat is. It's just the conditional mean. And this is the minimum MSE. Now if you stare at this for a second, you might recognize this as the conditional variance. Let me just highlight this. Okay, this expression, MSE min, the minimum one, is the conditional variance. So these are two very important manifestations of conditional mean and conditional variance. And that is pretty much all we have in this handout. It's just kind of going through some of the main concepts useful in this course in a way that tries to explain them in a textbook format, if that's helpful to you. Okay, so coming back to our slides, there's really only a couple more slides to present in this unit. And here's one of them. So this slide talks about the sample estimators. In particular, it talks about how good they are. What are their bias and what's their variance? So we're going to make this real simple. We're going to focus on a random variable, we'll call it z, it's just a scalar random variable. And we're going to say that it has a statistical mean of mu and a statistical variance of v. So let's say that, as in practice, we never know exactly all the statistics of the quantities we're dealing with in the real world. Instead, we are given many examples of them. And so a very common problem is to figure out what are the statistics, or to estimate those statistics based on the samples we get. So if someone gives you, a whole bunch of flips of a coin, they might ask you, is this coin fair or not fair? Like what is the expected value of the flip that it's going to come up with? So our first problem is to estimate the mean given independent realizations, little zi, where I goes from 1 to n, of this random variable z. So as we've talked about since Unit 1, a very popular thing is this sample mean estimator. And all you do is you take those realizations, zi, and you just average them. Call the result z bar. So the first question is z bar giving us the correct answer on average? And the answer is yes. When you look at the statistical mean of z bar, it is mu, which agrees with the statistical mean of the actual random variable. So that's great. And in fact, we call this z bar an unbiased estimate of mu. If you remember, we had our definitions of bias here. We say that a target y hat is unbiased if the difference between it and the true target on average is 0. Now in this case, here we have this conditioning on x. Over here we have a simpler case. We don't have features and targets. We just have targets alone. So we were missing the conditioning on x, but in that still, we just look at the average value of our solution and we ask whether that's correct on average. Okay, so this is an unbiased estimate. This is part of the reason why it's very popular to use. It gives you the correct result on average. But again, I want to emphasize that when you look at this sample mean z hat for a particular set of realizations, it's not going to equal mu exactly. It's going to be a little higher, a little lower, depending on the realization, but it's going to be correct on average. So because it's not correct every time you run it, you might want to know how much it deviates from the correct value, or another way is how much does it deviate from its mean. So for that, we want to evaluate the variance of this z bar. So by definition, the variance is the expected value of the quantity itself minus the mean of that quantity. And if you remember, we already derived the mean is mu, so that's why we're sticking that mu in there. So in a handout, we'll go through it, but in a handout, there's a derivation that shows that the variance of this sample mean estimator is v, which is the true variance of z, divided by n, which is the number of samples we get. So ideally, the variance would be as small as possible. Ideally, z bar is always exactly mu. Now, as you can see, that tends to happen more and more as n goes to infinity. So as my sample size goes to infinity, my z bar gets closer and closer to mu. But if I have just a few samples, then this tells me exactly how much this error, exactly how big the error is. And that's very useful. In fact, we use this in k-fold cross-validation. So in that case, instead of n, we call it k. And so we have these k different test folds. And for each test fold, we got an estimate of the mean squared error. And then we just did a simple average of those estimates to get our estimated mean squared error. And that's what we do. That's what we did in k-fold cross-validation. And then we asked the question, well, how much should I trust the results of that estimation? How much should I trust those z bars, or back then they were mean squared error bars. And this tells us exactly how much to trust them. And in fact, this is exactly the square of the standard error. This is the standard error squared. If you remember, the standard error is the standard deviation, which is the square root of this, divided by the square root of the number of average samples in the average. So this gives us the explanation for where that standard error equation came from. It's exactly this. Now there is one slight catch here, is that if we really wanted to use exactly this expression, we would need to know the true variance of this random variable. And when we do k-fold cross-validation, nobody tells us the true variance. So we can't use v exactly. We have to estimate v in addition. And so that's something we had to do. We had to estimate the standard deviation. And for that, what we did is we first used an unbiased estimate of the variance v, and then we took the square root of that to get it into the form of a standard deviation. So now we are finally at the point where we can understand what is meant by this unbiased. So remember, the unbiased variance estimator has the 1 over n minus 1 in front, whereas the other one, which we initially introduced in Unit 1, this has a 1 over n in front. And I told you back then that I'll explain what this all means later, and later means right now. So these are two reasonable ways of computing sample variance. The first one uses 1 over n, just like the sample mean. But it turns out, if you do an analysis of this, if you say, okay, I don't expect this to be a perfect estimate, but is it correct on average? Well, we can do the analysis. We can look at the expected value of SCZ, and unfortunately, it is not exactly v, which is what we would like. It is something slightly smaller than v. And how much smaller it is depends on n. So when you think about k-fold cross-validation, where n is really k, and you think about the case of k equals 5, which is a pretty popular choice of k, you would get 4/5 here. And 4/5 is quite a bit smaller than 1. So for that reason, a lot of people suggest not to use this biased estimate of the sample variance, but instead to use this unbiased one. And as shown in this handout, which we can take a look at, when you look at the expected value of this quantity, this is exactly the true variance of v. So that is the motivation for using it. This is biased, this is unbiased. So now you might ask, okay, so why would we ever use this biased estimate? Well, it turns out that there is a reason to use it. It actually has a lower mean squared error than the unbiased one. And to do that, we can do this analysis. We can look at the average squared difference between our variance estimate and the true variance. And with a bit of analysis, we can show that it takes on this value. We could do the same analysis for our unbiased estimator here, and we can find that it takes on this value. And with just a few lines, you can see that it's, in the handout, it shows that it's possible to see that this is going to be smaller than this. Okay, so we have sort of a trade-off here. Again, this is the bias-variance trade-off, but we're seeing it in the context of variance estimation. So if you really want something that's unbiased, then its variance will be larger. If you want something that minimizes MSE, it turns out that the best combination of bias and variance says to use something that is slightly biased. Okay, so that's sort of an interesting example of all this stuff just for estimating simple statistics. So let's take a quick look at that document. So this is what it looks like. So just to show you a few of the details here, a lot of this we already saw on the slide. So this is my sample mean estimator. Here's my biased and unbiased sample variance estimators. We say that these things are, we say that, yeah, an estimator of the mean is unbiased if on average its answer is mu, and we say that the variance is unbiased if on average its answer is the true variance v. In order to do the analysis, we're going to have to work out a few preliminary little things that will help us going forward. So imagine that I have realizations xi, where I goes from 1 through n, and we're going to think about all of these xi's themselves as random variables, but they all have the same statistics as this original x. So all of these random variables have a mean of mu, like this, and they all have a variance of v. So here's the first question. If I want to look at the mean of xi squared, what is that? Well, we learned in the in one of our earlier slides today that you can write the average value of the random variable squared as its mean squared times its variance. Now another question is, what if I encounter this expression? This is the average of xi times xj. Well, we have to know a little bit more about I and j. It turns out that there's really two cases to consider. When I and j are equal, let's say that they're both I, then obviously this is the same as this. And so in that case, we know that this is the correct expression. But when I and j are different, and because we are treating them as independent, then we can decouple this expectation into expectation of xi times expectation of xj. We know each of these is mu, so their product is mu squared. So those are really the two things that can happen, and we're going to express those in one expression using this discrete time delta, sometimes called the Chronicler Delta. And you can think of this as a function of k. Basically, whenever its argument goes to 0, it comes alive and takes on the value 1, while whenever its argument is non-zero, then the delta takes on the value 0. So you can plot it like this. It looks like a sequence of points on the integers here that goes to 1 at 0, but otherwise, for any other integer, it takes on the value 0. Okay, and using this, it just is a nice way as kind of a switching constant. Whenever I and j are the same, the argument goes to 0, the v comes out. Whenever I and j are different, then the delta is 0, and this last term goes away, and we just get mu squared. Okay, so we're just setting this up to make the derivations that come next easier. Okay, so the first thing to do, which is very straightforward, is to look at the average value of our sample mean, or sample mean estimator, the expected value. So we plug in the expression for our sample mean estimator. We use the linearity of expectation to pull the sum and the scaling out of the expectation. And finally, we have this, which we know from the previous page is just mu. So then we have the average of a sequence of mu's, which is just mu. Okay, so we figured out here that on average, the sample mean is giving us the correct estimate. It is giving us the statistical mean. So we say it's an unbiased estimator. Now, the next question is, can we do the same thing for our variance estimates? We have these two variance estimates. We would like to know whether they are unbiased or not. So if you remember, they have a very common expression. The only thing that's different is one of them has a 1 over n here, and the other one has a 1 over n on this, 1 over n minus 1 on that quantity. So let's just analyze this, and then we'll scale them later. Okay, so when we analyze this, the first thing we can do, again, by linearity of expectation, we pull this out, we get this, and now I need to look at this expectation. So what I can do is I can expand this quadratic. I get xi squared minus 2 times the cross product plus x bar squared. And by linearity of expectation again, this is the expected value of this sum of things is the sum of the expectations. So we get that. So now I have to do a little bit more work to see what these are. Okay, so this one we saw on the previous page, this is just mu squared plus v. What about the next one? This requires a little bit more work. So we want to look at expected value of xi times the sample mean. So what I'm going to do is I have to expand the sample mean like this. So first I want to point out something very important. When you do something like this, when we write this sum, we cannot use the variable I, because the variable I already has a very specific meaning. It's fixed over here. So because I'm reserving that to have a specific meaning, I cannot put an I here and here. That would be completely wrong. So I must use some other variable. We'll call it j. And so this obviously goes from 1 to n. All right, so now that I have that settled, what I can do is by linearity, I can move this outside the expectation, and we get this quantity. And finally, this is something we analyzed on the previous slide, gave it this term, so we have that. And the last thing to do is to simplify this. So if I look at the first term, you can see that this is just the average of mu squared times 2. So that gives us this. The next part is a little bit more interesting. So here we have, so clearly like the v can come out, but what is the average, or let's say what is the sum over all these j's of this delta? So remember that I is fixed and it takes on one specific value. So when I evaluate the sum, only one of these different j's will match I. And that one j that matches I will produce a 1 from this, and all the other j's that don't match I, they'll produce zeros. So of this whole sum, this thing turns into just v, and I get 2 over n times v. Okay, so what's important here is that this term has an n scaling, and this one does not. Okay, so that covers that case. What about this last case? We have to look at the expected value of the sample mean squared. So here's our sample mean, here's the square. And here again, we have to be careful when we expand this. So what we're going to do is we're going to write this as a product of two sums. But again, here's something that we don't want to do. Imagine that I write this as a sum over j times xj and another sum over j times xj. This is very dangerous because these j's are have a completely different meaning than those j's. And it might be tempting, once you write everything with the same j, to forget that and to write this as something like sum over j, xj squared. And it turns out that this is completely wrong. This is no longer mathematically correct because you have forgotten that actually these two j's are completely different. So they're not the same thing. So rather than doing this, so let me put a big X through that. Rather than doing that, what we want to do is we want to write this as a sum over, let's say, j, and then we have to choose another variable, anything except j or some other quantity that we've already used. We'll call it I. And now we have a correct way of writing this, and we can go one step further as we do in the typeface. We're actually going to write this as a double sum over I and j of xj, xi. Okay, so that's what we did over here. We wrote this as this. We also pulled out this 1 over n squared to the front. And now what we can do is we can pull this sum out. So that's double sum, and we have the expected value of xi times xj, which we found on the last page, equals that. So, okay, what's the next step? Well, this is just another fancy average. It's an average over I and j of this constant. So this constant gives us that, just mu squared. Next, what happens with this? Okay, So what I want to do is I want to take the sum over I and j of this. So here's how I like to think about that. Let's focus on this term. So if I make a matrix which contains the values of this for all I and all j, you can see that I'll have essentially the identity matrix. So if I have I going down the rows and j across the columns, then all the diagonal elements of this matrix, that's when I equals j, will give me the value 1. But all the off diagonals will give me the value 0 because I and j are different. So if I sum up all the terms in that matrix, I'm going to sum up the terms on the diagonal. There's n of them equal to 1, and I get exactly n. So that single n is going to cancel one of the n's in the n squared, and I'm finally going to get this expression. Okay, so what we've done now is we figure out all the terms here. We can put everything together, simplify it, and we get that this equals n minus 1 times v, and then as a result, we can put the appropriate scalings on them to make our two estimators, and we find that one of them is biased, the other is unbiased. Okay, so the next thing to talk about is, this is the one standard error rule sort of thing, the variance of the sample estimators. So let's come back to the sample mean estimator, x bar. So we'd like to know, for a finite set of examples n, what is the variance of x bar? Okay, so by definition, we have the variance is the expected value of the variable we want to analyze minus its mean, quantity squared. So we already determined that the expected value of the sample mean is mu, so that's there. We can expand this quadratic like this. We can apply linearity to take the expected value of the different terms. Of course, mu is non-random, so we can pull it out of the expectation. And finally, we have some terms that we solved for on the previous page. We solve for that. We know that this is mu. And we put everything together, cancel some like terms, and we finally find that the variance of the sample mean estimator is v over the number of samples n. So again, that's just a squared version of the standard error expression. So it turns out that if you want to analyze the variances of the sample variance estimators, those are more difficult, and you actually need to make more assumptions on the distribution of the x's. It's not enough to say that the x's have mean, mu, and variance v. So if you assume a convenient distribution like Gaussian, then with a bit more work that I'm not showing here, you can compute expressions for the variance of both of those. And what you can see here is that this is the biased one. This has a lower variance than the unbiased one. So here we see this bias-variance trade-off. If you don't want bias, you're going to have a higher variance. If you can accept bias, you have a lower variance. And we can, to optimize the bias-variance trade-off, you would say, let's minimize the mean squared error. So we can do this by looking at the mean squared error directly. So here is, this is going to be, okay, switching gears again, back to the sample mean estimator, x bar. We can look at its mean squared error using calculations, exploiting calculations from before. So by definition, the mean squared error is the estimate minus the truth squared on average. And we know whenever you have expected value of some random variable a squared, you can write this as the expected value of a quantity squared plus the variance of a. Okay, so in this case, a is just x bar minus mu. That's the random quantity. And so we have, here's the mean of that thing squared and the variance. Now, yeah, so one other thing, the variance of x bar minus mu is the same as the variance of x bar, because adding a constant offset does not change the variance. It doesn't change the deviation around the mean. So we're just getting rid of this minus mu, and this is just the variance of x bar. Okay, so how do we do this? Well, we can expand. We can just use linearity to say this is expected value of x bar minus expected value of mu, which is mu. That whole quantity gets squared, but this whole quantity is actually 0. So we're just left with, this goes to 0, we're just left with the variance, which we derived as this. And we can do a similar analysis if we want to know the mean squared error of the biased sample, Bias-Variance estimator. With a little bit of work, we show it's this. We can look at the mean squared error of the unbiased one. With a little work, we show it's this. And finally, using a sequence of inequalities, you can show that the biased variance estimator has a lower MSE than the unbiased variance estimator. So whether or not you want to use the biased or unbiased one depends on what's more important to you. Is bias more important to you, or is mean squared error more important to you? Both are pretty commonly used. So they're both good choices. It just depends on the application. All right, so I think that covers what we have on this slide. And the only other handout, I'll just briefly mention, there is one other handout, and this handout is on the bias and variance analysis of multiple linear regression. So going back to the slides, if you remember, this relates to this page. So for the bias variance formula for least squares linear regression, what we said is that we have a true model that, as you can see, is linear with d true coefficients, whereas the a predicted model, it has the right form, but it has a possibly different number of coefficients, which is d. D might be smaller, larger, or equal to d true. It just depends. Also, clearly we have different coefficients too. We have beta hats here versus the true beta. And we're going to assume that the beta hats were computed with least squares estimation, least squares regression. So we saw some important results. Let's focus on this one here. If d is less than d true, then we will have bias due to underfitting. Our model is too simple for reality. On the other hand, if our model has greater or equal to complexity as the truth, then we find that our prediction is unbiased. So on average, y hat matches the true test sample y, but that doesn't mean that on any given realization it's going to match y. It's not. It's just on average it matches it. So what we also have to care about is how far does y hat deviate from itself on average, and that is the variance. And what's done in this handout is analyzing this equation, which is very interesting. It shows that the variance rises proportionally to how many features are in your chosen model divided by how many training samples are in your data set. So this shows us the penalty in least squares linear regression for using too many features. It doesn't hurt you at all in terms of the bias, but it does hurt you in terms of the variance. On the other hand, it also shows you the value of having a large data set. The larger your data set, the smaller your variance becomes. This is a training data set. Okay, so all of this is done in this handout, and I'm not going to go through the details here, but it just gives all the details for that. It shows the bias and variance and so on. So it's a little bit more involved than some of the other ones, but I wanted to provide it to you because I didn't see a very good explanation of this in any of the books. So thought you might find that handy. All right, so the very last thing, which we can cover very quickly, is really just a prelude to the next unit. So until now, we have focused on model order selection. So an example, if we're talking about a linear model, would be, okay, do I use this simple model with one term, or do I use a more complicated model with two terms, or do I use a yet more complicated model with three terms? And as you can see, the number of different choices we have just grows linearly with the complexity. It grows linearly with D. D is, this is D equals 3, D equals 2, D equals 1, because we just have 1 or 2 or 3 coefficients. Okay, but someone might say, that's not really the right question to ask. Maybe the right question to ask is, exactly which features should I use? Maybe I shouldn't have to use all of these. Maybe I really want to use just x2, or maybe I want to use just x1 and x3. That problem is called feature selection. And yes, if you do feature selection, then you actually get a lot more possibilities than model selection, and therefore you should be able to do better. But the number of possibilities is what's challenging. So for example, if we talk about this last case where we have 3 possible features to use, and let's say our data only has these 3 features, we actually have 8 different possibilities of models we could come up with. One case is just to use x1, another just to use x2, a third just to use x3, a fourth use x1 and x2 but not x3, fifth use x2 and x3 but not x1, sixth use x1 and x3, seventh use all of them, or eighth use none of them. So in general, what you find is that there are, if you have a total of D features, you have 2 to the D possible subsets of features, and therefore 2 to the D possible models you can come up with. So when D is a small number, like less than 10, that's not a big deal. You can probably evaluate every single one of those models using cross-validation and choose the best one. But once D gets to be larger, 2 to the power D becomes a giant number, and it becomes impossible to check them all. So in that case, we need to do something different. We need to come up with some approximate methods for feature selection, and as we'll see, there's a whole number of them, and they have advantages and disadvantages, but that will be the subject of the next unit. So that's all we have for today, and I hope you guys have a good weekend and look forward to seeing you next Monday.